Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so good morning. Thank you for coming here. And it's a pleasure to me to introduce our speaker. And let's start with an anecdote. This summer, we ran with me and Manuel Fanducci, we ran SAS, and we had the same person as invited speaker. And the session chair who introduced him, Nicolas Olbachs, was kind of angry with me and with Manuel, because he said, okay, in introducing the invited speaker, it's a big honor, but an invited speaker with such a long name, it's hard to introduce. And now I understand why Nicola was a little bit nervous, because I have to pronounce his name. So it's Sriram Sankaranarayanan.
Perfect.
Yes! Yes. Well, I have to say that I read it, but to be honest, Nicola, he learned by heart his name, so I spent all the evening, probably the night, doing it. Okay, no, stopping with jokes. I think everyone knows Sriram. He did great contribution in the field of verification, static analysis, and I think everyone knows about templates. Then were introduced by Sriram, and all his work he made on numerical domains when he was in his PhD with Zoharman and was you the co-advisor to NECIPMA, and then he moved to the industry, NEC, where he worked on a real software static analyzer, used at NEC from my understanding, and then continued his career at the University of Boulder, which now he's trying to prove that human body is correct. So you're trying to verify human body or something like this, probably.
I hope so, but we'll see.
That's good. Okay, thank you.
So, yeah, thank you, Francesco, for the kind invitation, and thanks for having me here. I've had a wonderful time yesterday, and hopefully, it promises to be a great day. But today my talk is about this title called Optimal Falsification for Cyber-Physical Systems. Some of the slides in the talk it was a talk given to a broader audience, so some of these slides are going to be childish, so I ask you to forgive me for that. So what are cyber-physical systems? So we all have an idea of what cyber-physical systems are. These are systems which interact with the environment. So these are software systems that have a physical component to them. So if you think of an artificial insulin delivery system, it controls the human body, which you can think of as a physical or a biological system, through a software that controls how the infusion pump infuses insulin. Software is becoming a huge deal in automotive systems, where a lot of functions that were taken over, that were done by mechanical parts, are now being software controlled. It's called drive-by-wire. Software is coming in a big way to the power grid, like active microgrid power systems, and these are very important. So it's very important for us to get the software correct, right? But it's very difficult as well to get the software correct. So I thought I would go up to the National Highway Transportation Safety Association, and they have a bunch of recalls, and just get a couple of the recalls, as small sampling of software related recalls. And you can find this if you do Bing on automotive software related recalls. And one of them says, okay, due to a software problem, the door may unexpectedly open while the person is driving the car, which seems like a very strange thing. What does software have to do with the door of a car? But it's a security system in a car where software controls whether a door opens or closes. And now the door can open while the person is driving.
No problem if you're wearing your seatbelt.
Right.
Can take fire. You see the Tesla took fire yesterday?
Sure. So okay, fine. No problem if you're wearing a seatbelt. But now look at this one.
Let's just say another reason to wear your seatbelt.
Perfect. Another reason to wear your seatbelt. But look at this one. So this one says, so for the electric motor to rotate in the direction opposite to that selected by the transmission, due to a software problem. Now I'm not, the reason is not because they don't know how to build software. It's just that when you build it, there are so many bugs. And you may ask me, okay, we've been doing software verification for the last 20 years. What's different about these bugs? Two things are different. These are functional correctness properties. These are not buffer overflows. These are not null pointer errors, which we know how to take care of. And hopefully, there will be no more talks on these subjects of null pointer errors, buffer overflows, thanks to all the good work you guys do. But there are still going to be these bugs left, so our job is not done. And these are properties of the closed loop system. These are not properties of just the software alone. These are properties of the software and the physical environment, the physical artifacts that it controls. Without talking about the physical artifacts, you cannot just verify this inside the software. That's the main point I wanted to make with this.
So a car is really no longer a car. It's a computer with wheels.
That's right.
I think is a good way to think about
That's absolutely right.
Everything you knew about a car from sort of racing go-karts is actually completely falsified, can be completely false about an automotive car now.
Exactly. A modern automobile is becoming more and more electronic.
It used to resemble a go-kart. So if you were in a go-kart, you would be like, oh, I'm playing like in a car, and then you got in a car. And it was actually very similar in some sense, right?
Yeah.
Because it was physical.
And most cars, you press the brake, you're just sending a signal to a computer that's going to then control the braking system. There's no direct connection between your brake pedal and unless you really have a very old model of a car. There's no direct connection between the brake pedal and the drums. There's no mechanical connection anymore.
As I understand from it, won't roll if it has no power. So Teslas get bricked if the batteries drain, it's impossible to roll the car.
Right, probably. Yeah, I mean, these are, and there are systems like the Boeing's, the latest Boeing aircraft can actually override the pilot. The autopilot can override the manual pilot. It used to be the other way around. So now they place more trust in their computer systems than on the human. So things are very interesting. And where is verification in all this? So, and what is stopping us from just solving this problem with all the tools that we have? So that's going to be most of what my talk is about. So I'm going to come up with somewhat a different view of what we can do as a first step towards getting verification on the track. Someone has to start and something has to be done. So as a first step, we are going to try and approach the full force of this verification problem through model-based design. And I'll show you what we have done so far. Okay, it's going to be very simple. It's mostly testing, pretending to be falsification. So I'll talk about that. And I'll give you a couple of case studies on which we have had some initial successes. So we haven't solved anything, but we have hopefully made a step towards thinking about these problems and solving them. Okay. So the first challenge when you think of these systems is modeling. So what do you need to model? You need to model the computation, and you need to model how this computation interacts with the physical subsystem. But this is nothing new. We know about hybrid automata. A lot of people pioneered this in the 90s, and we've spent 15 to 20 years looking at hybrid automata, maybe more than that, 25 years looking at this hybrid automaton model, which has these states. Inside each mode, there's an ordinary differential equation that says how things evolve inside the mode, and there are these guards that go from one mode to another, right? And we know hybrid automata. We know what's decidable, what's undecidable, how to model check, how to do static analysis, and to no end. But all of this is no good when you come up against this beast, which is called a Simulink Stateflow diagram. And if you go into the industry, this is what people do their development in. It is equivalent to a hybrid automaton. You could prove the theorem, but it's going to be a hybrid automaton that you cannot write down. It's going to have more modes than the number of atoms in gas at standard temperature and pressure, right? Because these are not easy to translate to hybrid automaton, and a lot of work needs to be done. So what stops us there? Well, they could have continuous input signals. They have discrete switching, of course, otherwise they don't become hybrid. They have continuous dynamics. So each of these blocks with a picture just expands into a huge block when you double click on it, right? They are non-linear. Linear systems are much easier to deal with. And to take the cake, the semantics are unclear, but that's not the huge problem. You could say that the semantics are unclear in some corner cases. It's quite clear in many of the cases, but there is inadequate documentation. It keeps changing from version to version, and there is very little front-end support. This is not the world of C or C#, where we have nice front-end tools to parse these things, to load them up, and intermediate representations to simplify them. We have to tackle these diagrams in the full force of the diagrams, right? They are really hard to deal with as a static analysis inside a static analysis infrastructure, and so there is none. There is no static analysis infrastructure.
Apart from the right top corner, the rest is within the expressiveness of hybrid automata, correct?
It's within the expressiveness of hybrid automaton, but it's outside the expressiveness of most verification tools. So when they start to combine arbitrary functions that are defined by tables and so on, most verification tools are not able to do them, and they compose these functions to make huge functions. So they can very easily defeat our verification tools.
So it's not even about decidability, it's about practical.
Yeah, decidability barrier is very low. 2 variables in a hybrid automaton is already undecidable, right? 2 modes. I mean, we know all those, from the 90s, we know what you need to get to undecidability, and nothing, really, very little, right? These are like well into the undecidable frontier. So nothing, definite can be said about verification or falsification, but we still try, right? It still doesn't stop us from trying. Okay. So the goal for this talk is I'm going to try and verify these complex systems, but I'm going to use simulations as the only way of obtaining information about the system. So given upfront, let's restrict ourselves. I mean, this is a harsh restriction, unnecessary, but let's still restrict ourselves with this. Let's say simulations is the only thing that we can do. Then can we still do something that's better than randomly testing the system? That's going to be my premise for this talk. So it's going to be, hopefully nothing deep, but let's see how much we can get and where do we, break when we start to simulate. And this is something like black box falsification. You're treating the system as a black box. That may be bad, but it's convenient to do so because we can start to get tools that work on real models right up front. So it's a very practical thing to do. So we will presume that any system they give us is flawed, and our hope is to search for this violation systematically. If we find one, it's going to be golden. We can go to the developer and show them the violation. But if we don't find one, then we have done our effort. We've run for many days. And that's what most model checkers do anyway. After running for many days, you still may not exhaustively have exhausted your state space. So you press Control-C and stop the engine, right? In many practical model checking examples, that's how you end. I mean, if you look like explicit state model checking with spin, you never finish on big examples. You find a violation or it just keeps running and you just gain confidence by it's run 5 days and found nothing. Okay, so the big question then is where should we search and how should we search? So ideally, I would like to use an SMT solver and use BMC. We all saw the talk yesterday where they did Corral and they did some nice unwinding and gave it to an SMT solver. And SMT solvers have inspired a lot of our thinking process, but we are nowhere close to doing this because we would immediately get into nonlinear theories and immediately get into trouble. Okay, so there are 2 ideas that I will present. One is we are going to reinterpret temporal logic, and I'm going to call this the robustness interpretation of temporal logic. So what temporal logics, the logics we study, is they take a trace and they give us true or false. Is this a property violation or is this not a property violation? But what we are going to do is reinterpret it with real values, and we are going to do it in a systematic way where properties can be proved, the Boolean interpretation can be compared with the real valued interpretation and so on. So we are going to systematically do that. And once you change a Boolean value to a real value, what we will now see is it's very natural to use optimization as a search procedure. And some very interesting properties of cyber physical systems can be exploited once we do that. So I'll show you how those 2 things can be done. And I'll show you some better ideas on how to do this search that are also inspired by thinking about how SMT solvers do this search. So I'll give you some flavor of how we are proceeding with that. Okay. So let me start with the robustness interpretation. So this was work that was originally started by Georgios, and then I joined with Georgios on doing this robustness interpretation. So I think it's a very cool piece of work. I really like the way the issues have been brought out here. So the way the standard picture works is, okay, I already told you we have a simulator. It produces a trace that goes into a property monitor. Now think of your property as an LTL property or a metric temporal logic property or a real-time temporal logic property of your choice. And the property is monitored and you get a true or a false. And we are after false. That's why we are doing falsification. Okay. Now let me take an example to motivate this. So in this example, this is a very simple example, but it's also a complex example in another way. This is a small example, but it can produce very complex behaviors, and it's called a Van-der-Pol oscillator. I just brought it up. So the green or the blue box are the initial states, and our goal is to find a trace that reaches the red box. Okay, and I have shown you around 10,000 or some such number. I've shown you that many simulations, and you can see that the property is clearly violated. So this is not meant to be a tough problem. It's meant to illustrate what we are seeing. Okay. So hopefully, if this is clear, the details of the system are not too important to us. This could be any system. Okay. Now let me do this plot to motivate what we are after. So this plot just says the bottom, the x and y axis are going to be our initial conditions between minus 0.5 and 0.5, minus 0.5 and 0.5. For each initial condition point, I plot plus 20. The plus 20 is just to make MATLAB show it as a big, z-axis. Plus 20 if it's true, and it's shown up there in pink, and minus 20 if it's false, and it's shown down there, and you can see the thing down there. Okay. Now if you look at, this is our search space, and I visualized it for you. Okay. The search space looks quite flat. So if you're an ant at the top, right? So and you randomly choose a point, with very high probability you're going to land in the pink zone in the top, right? But if you're there, you don't know whether to go left or whether to go right. Which is the direction should you search towards falsification? Okay. And such a question may not make much sense in program verification, but it makes a lot of sense in cyber physical systems, because you always think about, suppose I've tried input 0.5 and 0.4, then should I try 0.6 and 0.5? You always think about the neighborhood of your input space. That's how you think, right? So in a program, in a programming world, the nearby inputs could produce something wildly different. But in a cyber physical system, you expect it to produce something similar, and that's called continuous sensitivity to initial conditions.
Here you want to just put some ping pong balls on and shake it, do some simulated annealing, right?
That's right, and that's where.
Hop over into the clip.
That's right, but if you do simulated annealing on this, it's just going to do random search on the pink zone, right? Because the way the search space looks is it's a cliff, and you don't know where the dropout points are, right? So this is the first thing we are going to do. We are going to change this. We are going to change how we view this, and we are going to say, does a trace violate a property is a Boolean interpretation. We get to how close does a trace get to violating the property. So what's distance between the trace and the property, and can we define this distance systematically? And if we do that, if we manage that without bringing in an arbitrary definition of closeness, we have to make it systematic, or else we would get something that looks quite random and won't give us the answer we want, right? So to motivate that idea, let me take up two traces. Okay, the bottom left corner, the circle there is the initial condition, and there's two traces, trace 1 and trace 2, and the red box is what we need to hit to violate the property of our interest. Okay. Now you can look at it and you can say, oh, trace 1 is so far away from being a violation, but trace 2 is so close to being a violation. Okay. But the Boolean interpretation is hiding this, because it just gives you true for both traces. It doesn't give you any more information other than how close to being false. But can we make it a definition that actually gives us how close a trace is to be false? And we can do this for the kinds of systems we are interested in, because the state space is real valued. And what we define here is the notion of a robustness of a trace, which we say is the radius of the cylinder around the trace, okay, so that any other trace in the same cylinder that you can think of has the same valuation as the trace that you are interested in. So in this case, the blue trace has a valuation of true for the property, that I do not hit the orange region. And therefore, I put this cylinder around the blue trace, and you can see how the cylinder is quite natural. It's, it's formed by making sure that its boundaries just touch the unsafe region. And then any other trace, like the orange trace that I have shown, that lies inside the cylinder has the same valuation as the property. Okay? And the radius of the cylinder is the number that we will call robustness. If the property is true, we will make it a positive number. If the property is false, we'll make it a negative number. Okay, so this is basically the formal definition of robustness. And the nice thing that we can now show is the following. So we can define robustness as a function that takes traces to real numbers. Okay, and the idea is we connect it up with the Boolean valued semantics like this. So if the trace satisfies the formula, the robustness is made strictly positive, and we ensure that it's strictly positive. And if it's strictly negative, then the trace doesn't satisfy. If it's 0, then there is it's actually a corner case where the trace either could or could not, and that's one of the problems with this definition. But it's still so rare to get exactly 0 that we don't worry about it. Okay, so we make, instead of Boolean semantics, we now go to real valued semantics. But how is this real valued semantics defined? And the cool thing is you just take the way you defined your Boolean semantics and you change a few parts of your definition and out comes the real valued semantics. So how does that work? So instead of saying whether a point satisfies an atomic proposition P, you look at the signed distance between the point, the state, and the proposition. Okay, so distance between a state and a set is well defined, and you can sign distance means that if the state is outside the set, it's a positive number. If the state is inside the set, it's a negative number. So instead of being, saying does a state X satisfy an atomic proposition P, you say what's the distance from X to P. Okay.
So or the distance between the point and the set is the distance between the point and the frontier of the set.
Of the frontier of the set.
So it's not.
It's called the Hausdorff distance. You say.
But you can have three forms, isn't it? You can have the closest, the farthest, or the average.
Right. So this would be the closest.
The closest.
Yeah. So we use the closest distance from the point to the frontier of the set as the point set distance. Okay. And we make it signed to give us the negative robustness means violation, positive means satisfaction. So we make sure that the sign convention respects that. And now OR becomes max, AND becomes min, negation becomes taking the minus of the robustness, and things like Boolean operators like box, if you remember from temporal logic, they can be expanded out into OR and the what holds in the next state. The same thing now becomes, OR becomes max, AND becomes min, and so you immediately get the recursive definition that you are really interested in. Okay, and everything works out nicely. So you just change OR to max, AND to min, and you change the Boolean operators accordingly, and negation becomes a minus. So and then you get the robustness. As long as at the atomic proposition level, you look at sign distances. It's a very interesting, just a very simple modification of how you think of temporal logic, and suddenly you get this number that makes a lot of sense.
This is a big question about sign distance too. Which are the properties of sign distance you have that? So, for instance, does it also the triangular property for a sign distance?
Yes, it has to be a metric.
It has to be a metric. Okay.
Yeah. So we make sure it's a.
Everything you drop is distance x, y. It's always going to equal to 0. That's
correct. Because we use a signed. Okay. If it's inside the set, we kind of give it a negative sign. But our distance has to be a metric. We have a paper in which we show that even if it's a quasi-metric where we drop one of the requirements of being a metric, it still works. But yes, you're right. It has to have those topological properties, or else this doesn't work. Yeah, you get some nonsense otherwise. All right. So what we then do is the following. Okay. So what's the computational complexity of computing the robustness? Well, it's linear. It's almost the same computational complexity as evaluating the formula on the trace, except for a small change, which is instead of doing whether a point lies inside a set, you have to do the distance computation. In the general case, it's a convex optimization problem. Okay, depending on how distances are defined, L2 distances or L1 distances or L infinity distances. But there are some special cases where the atomic propositions are just boxes or hyperrectangles. Things remain in a certain range is an example of a hyperrectangular predicate. Then we can make this distance computation rather fast. And so this would be, would have been a bottleneck, but we can make it rather fast and make sure that we restrict our logic formulas to make the distance computation fast. Okay, and we have a tool, or I should say Georgios has a tool called Taliro, which computes temporal logic robustness for MATLAB traces, and we have extended that to hybrid system traces as well. So that was the first part of getting a distance, and let's see what has that achieved for us. So go back to the Van-der-Pol example. We had this 0-1 surface which wasn't helping us a lot, especially when we were trying to do simulated annealing. Instead, let's do robustness, and immediately you get the surface on the right, which now has some interesting features. So it's very hard to see from this projector, but what you can see is that on the right hand side, on the right hand top corner, things are elevated.
Your right hand side or?
Oh, sorry.
Our left hand side.
Your left hand side. Sorry. Your left hand side top corner, you can see things are elevated. You can see that there's a peak in the center because the system has an equilibrium in the center. It just remains where it is. And so robustness is pretty high there because it goes nowhere near the unsafe set. But you can see how the violations, the two red arrows that I have shown, correspond with the violations here. But there is a gradient that informs how you get there. And so you can do simulated annealing on this surface, and you will get a lot better performance empirically than on this surface, where it will just behave like a random walk on the surface. So that was the main idea behind using robustness for falsification. So again, it's nothing deep, but we are just building on what is the minimum that we can do and what's better than that minimum, right? So again you start with your property monitor, out it goes, and in comes robustness computation. So you have these robustness computation tool Taliro, and what you do is you hook it up with an optimization of your choice. There's no silver bullet here, but we tried many different optimization solvers, and each one of them works well on an example. It's the same problem that Coral has yesterday, which is, or SLAM has, which optimization do you run? You just run all of them if you can, right? And that's what we do. There's a bunch of these tools we can run, starting with simulated annealing. We have a method called the cross entropy method, which is a stochastic optimization method. You can even run genetic algorithms and colony optimization. We just threw it, whatever solvers we had. There are no guarantees on performance, which, if you know my research, is not how I like to operate. But this is the world of, we started from ground zero and we said we were going to solve a hard problem. So let's do it from ground zero. Let's get the low hanging fruit out of the way, which is, I guess, put an optimization solver and let it find a falsification. Again, we actually got very good results from this, very promising. We managed to falsify examples which you cannot even get started with any other method, because we are very simple. We are just testing, and we just have this optimization loop, and robustness is the main thing, the secret thing that gives us the power to test it, because it gives us a gradient, it gives us a direction, go this way and test this way, and that gives you better answers. Okay, so just to illustrate one case study where we got some good results. So this is an automatic transmission model that was proposed by two researchers then at Ford Motor Company. Now Ken Butts is at Toyota, and he proposed this as a tech report of a challenge problem that people in the hybrid systems community should try and solve. And he gave, so this system it models a powertrain, which roughly speaking is, it takes the current throttle position, like where your accelerator pedal is pressed. You can think of it that way. The initial speed and the road grade, like whether you're going up or down, and it adjusts the torque that the engine provides to the wheels, and the shift schedule, which gear should I shift? Should I be in the first gear or the second gear? Which gear should I go to make sure that I'm not stalling or falling back, right? It has 6 continuous state variables, 24 discrete modes. It's not a very complicated system, and it's by no means the most complicated system we have looked at. And its dynamics are fine, but it's still complex enough to defeat most of the tools out there. Okay, and we were given some properties like starting from 0 speed, if the vehicle shifts from the second gear to the first gear and then back to the second gear, is that even possible? Or they asked us, if the vehicle shifts into the first gear, it will not shift back into the second gear for at least 2.5 seconds. It should remain in the gear that it just shifted into, and it shouldn't just keep like shifting back and forth. And they wanted to know if these properties were false. For example, 2, it wasn't known. It wasn't very well known whether it was true or false. And what we found out was it was actually false. We found a falsification. We actually falsified all the 3 properties out there, okay, using S-Taliro. And here is an example of what the robustness looks like. We managed to plot it for this example. It's just fixing the values of some of the variables and plotting for the rest. And you find that that's the overall figure on to my right and to your left, where you see that yellow region at the bottom. In that little yellow region, if you blow it up, you will see another little region here where the robustness goes negative, and you will find a violation. Elsewhere, there is no violation. Okay, so drawing this figure takes a lot of time, because you see each of these little dots is a simulation. But S-Taliro just samples a small part of the space and gets there. Okay, it's around 700 simulations, but this figure itself took around 10,000 or more simulations. So even though this figure is misleading, you could say just watch this figure. There's a violation there. S-Taliro has to find it without drawing this plot. This is just for your illustration. And the nice thing is, because this is a testing method, we can provide them the test inputs that show, okay, do this, and this gives you the falsification. So it was very easy for us to convince the people who had formulated this model that there was a violation, because we just had to send them over our signals. So that was nice. Okay, so the tool is actually available. It's called S-Taliro. I'll give you a link, and it supports Simulink stateflow models. That's very nice, because it lets a lot of people adopt this tool, because we actually support something that they use. We have tried it on many challenging examples, some automotive examples, closed loop models of medical devices. I'll tell you a little bit about them. And One of the projects I used it for was on searching for failure modes of insulin infusion pumps, where we looked at how to find failure modes of this model and how to do parameter synthesis of patient parameters and controller parameters using this kind of search. So we are also trying to get into some synthesis using S-Taliro. But what I will do, instead of talking about these examples, is I'll look at something that was actually inspired by the way SMT solvers work, and that inspired how to think about falsification a little bit more. And what we now call this multiple shooting methods. We initially called it trajectory splicing, and this was inspired a little bit by thinking about how would an SMT solver approach the problem of falsification. And multiple shooting is a name that the control theorists said was the standard name for it, rather than trajectory splicing. So that's why we called it multiple shooting. So what is multiple shooting and what is single shooting? Okay, and single shooting is a term that says we fix all the initial conditions and all the signals and then simulate the system to find a violation. And that's how S-Taliro does its search. It needs everything, all the inputs, and then it runs a simulator, then it obtains a trace, and then it finds a violation. And you might be wondering, is there any other way to do it, right? The other way to do it is like this, and this is partly, I said, inspired by SMT solvers, which is you find small segments of traces, okay, little segments of traces that can be disconnected, and you try to join them up, okay, and we call these segmented trajectories, and we call the process of joining them trajectory splicing, okay, and the magic is when you do things this way, you can get much faster on some of the benchmarks, and let me explain what this is doing. So what this is saying is, if you can think of choosing the initial conditions and all the signals as saying, let's solve a satisfiability problem by upfront fixing the entire model and then seeing if the model satisfies the formula. But SMT solvers don't do it that way. They come up with partial assignments that fix parts of the model and see if they can learn conflict clauses, backtrack, and then come up with, so they don't search the entire space upfront. They search for partial assignments and see if that backtrack. So this was a very naive way of saying, let's also search for partial assignments. Let's look for parts of a trajectory and see if we can join them up to make a full trajectory. Okay, how does this even work? So the way this works is like this. So what we have is, suppose you have these split trajectories where there are gaps between the segments. Okay, what we will let the solver do is search in the space of these split trajectories, but use these gaps as a cost function. Okay, and I'm just showing you the version for safety. You can also extend it to other temporal logic properties, but I will not complicate the presentation here, right? So you can minimize, if you can minimize these gaps and eventually get them down to 0 as part of your optimization, then in the end you would have a complete trajectory where the state at the end of a segment will match with the state at the beginning of the next segment, and you will be able to join everything up. Okay, so there are some nice advantages to setting up the problem this way in multiple small segments that you can join together and get a violation. So what our tool does is it starts with some such segment that it finds through random simulation. So it will randomly simulate the system for part of the time, and then just take a random jump, randomly simulate the system, take a random jump until you find violation, and then it will join together and find a trajectory with gaps in it. But you can't give it to the user because this is nonsense right now. But if you can narrow the gaps recursively using optimization, then you can give it to the user. So that was the whole idea. And our hope was that we don't even have to narrow the gaps down to 0. If we can get it below double precision, then what does the user care? If the user can't see it in their simulations, if it's below the precision of a floating point number, then we are done, right? So we use that as an heuristic to say, let's narrow it down to 10 to the minus 10 and then give it to the user. The user and the simulator will usually be able to reproduce it. Okay, so that was the idea. How does this work? It's very standard actually. So what we then do is we set up the optimization problem like this. So we say the cost to minimize is the distance between the end of one trajectory, which is xi is the starting point of a trajectory, ti is how much time I spend, and f is the system simulation function. Okay, so I say that the gap between the end point of one trajectory and the beginning of the next trajectory, the sum of all these distances becomes my objective. Okay, and what we can, sorry?
Usual distance.
So usual distance. So we do L2 or L1 distance, but in this case we do L2. Yes, usual distance, not signed anymore. We are just looking at safety. I'm not giving you the full picture here. And what we now do is you can compute the gradient. So we can actually compute the derivative of these things with respect to xi with respect to xi plus 1, which sounds very surprising, but it's actually possible to do so, and in our paper we derive it. It's based on some very standard ideas in ordinary differential equations. Okay, so we do the derivatives, we can also calculate the second derivatives, and what you get is something called ordinary differential equation sensitivity analysis that can give us the derivatives, that can give us the second derivatives, and now we can use techniques that are well known in optimization like Newton's method or gradient descent to try and narrow these gaps. So we use random simulations, set up an initial state for the solver, and just let the solver go and narrow the gaps down to 0. Okay, and it's pretty good at doing that. And there are some functions, we don't have to implement all of this. These are all so standard in optimization that we just take a function like fminCon in MATLAB and just give our tool to fminCon. But we also have to give it the derivatives, which we calculate. We also have to give it the second derivatives if we want to use Newton's method, which we also calculate. And once we finish those calculations, we can give it fminCon. And what it does is it uses our calculations and finds a violation. Okay, or at least tries to find a violation. If it fails to do so, we just again randomly simulate, try another initial seed, try to see if it finds a violation, and so on. Okay. So let me just illustrate why one would want to do this kind of a technique on a different case study, and this case study is a small example of an artificial pancreas controller. It's not the latest one, it's an early example, and I'll tell you what stops us from doing the latest one just in a few minutes. So here the idea is we are looking at a control system that's controlling an insulin infusion pump that's pumping insulin into a patient who is type 1 diabetic, so it requires external insulin, and the patient has a variable glucose sensor which is sensing the level of glucose in their blood, and the controller looks at the level of glucose and decides how much insulin the patient needs to get. So it's a closed loop controller, and it's called the artificial pancreas. Okay. And in this, what we have is we have mathematical models of insulin glucose dynamics in the human body. So the human body has a very nice way of regulating glucose through insulin, and this dynamics is well understood. People have spent around 30 years modeling the dynamics using differential equations. So that part is well understood. So we just take one of those models. And people have also thought about control algorithms for controlling the flow of insulin. So we also use one of those control algorithms, and the input to such a model would be the caloric intake of the patient, what is the patient eating, and the output would be the blood glucose level G of t that the patient has currently. Okay. And for some more specifics for the insulin glucose dynamics, we just use for our examples a very simple model. It's called the Bergman minimal model. It has some deficiencies, but it's pretty good for trying to experiment with these systems and see how well our solver does on them. Okay, and we looked at a couple of control algorithms that were published in 1985 by Furler, 1991 by Fisher. So we went to their papers, fished out their control algorithms, and just implemented it in our closed loop. And what we did in this case was we took 21 different instances of parameters. So if you go back to this slide, the insulin glucose dynamics is governed by some parameters, some numbers, magic numbers that come from various patients. So what people have done is looked at patient studies where they have looked at the insulin glucose levels in a patient over time, and they have adjusted these parameters so that the model fits what the patient actually shows as real data. And there is some 21 different instances that are available. With the Bergman minimal model, you can get these instances for 21 different patients or virtual patients. So what we did was try to see, does the controller work on each of these patients, right? And what are we testing? What are our properties here? Properties are two safety properties. One safety property says hypoglycemia shouldn't happen, which means that the blood glucose level should not dip below 3 mmol per liter, or it is like 50 mg per dl, and that's the limit below which if it goes, it becomes very dangerous. So you should not let the blood glucose level go below that. And hyperglycemia, which is blood glucose level should not go above 22 mmol per liter, or roughly around 360 mg per dl. Okay, and we had some very interesting results here, and let me take the time to explain these results a little bit. So on the left, we tried 21 different patients, and we found 6 examples of violations. Okay, 5 of them were hyperglycemia violations. If you go back, the level of glucose greater than or equal to 22, and 1 of them was hypoglycemia violation, which says that the controller is pretty robust against parameter variations. It's not too bad, because I would have expected to see violations in all 21 cases, right? Now let's look at these violations a little bit detailed. So you can see the times we took in seconds, which is roughly like 1 second. In one case, we took 8 seconds. So that's not too bad. But I have another metric here, which we call the degree of difficulty, which is we tried 10,000 random simulations, and we saw of the 10,000 how many gave us a violation. That gives us an example, a metric of how difficult is the property to violate by our straw man. Right? If random simulation is a straw man we have to beat, then how does random simulation perform on this? So you can see out in 3 of these examples, 10,000 simulations yielded nothing, right? And in 2 of these examples, it yielded around 293 out of 10,000 and 84 out of 10,000. So probability wise, just by chance finding these violations is pretty hard. Okay. Now the interesting thing is we actually do find violations even when random simulation completely fails to find one, or it's pretty rare to find one through random simulation, right? And some other interesting things are, okay, so random simulations in these examples takes around 2 hours to finish. So 10,000 simulation takes around 2 hours to run, because simulations aren't cheap, they are also expensive, and this 2 hours is on parallel 4-core machine. So it's not, even, so it's all parallelized, and even then it takes a long time to finish. And we have a lot more benchmark results like this in our CDC paper. We have one more example called the NAV example, where we show very similar results across many instances of the benchmark, where random simulation takes a lot of time, whereas we can find a violation fairly fast, okay, which is very interesting. So we get, and we also get around 5 to 100x speedups when we do the same thing using single shooting. If we don't do this multiple shooting and just do single shooting, we get some very impressive speedups. And we also tried S-Taliro with simulated annealing, and we also get significant speedups on S-Taliro. When we do this multiple shooting method, we get some very good speedups on S-Taliro. So this is a very promising idea, but we still haven't managed to make it work on Simulink and Stateflow, primarily because Simulink and Stateflow makes it very hard for us to do these segmented simulations. You can't do a short simulation for a short amount of time, reset your simulation, then do another short simulation. That becomes pretty hard for us to automate in Simulink Stateflow. It insists on recompiling the model, so it's a technical issue that we just have, so every time we do it, the model compiles again, so that makes it very hard for us to make this worthwhile. Otherwise, the simulation itself just swamps up all the cost of doing work for us. So that becomes harder, and computing these gradients and Hessians in Simulink Stateflow still requires some support, which they aren't providing yet, but there is some hope that they will provide it soon enough. So what's the future work going to be? So the future work is, we really want to expand on artificial pancreas verification, and we really want to make sure that this verification can help people who are developing the artificial pancreas, which is an ongoing effort in many academic labs. Some industries have also started looking into the development of artificial pancreas. It's a huge industry. There's a lot of money that has been invested. Billions of dollars have been invested in type 1 diabetic research. So this would be a huge deal if we can get these things to market faster using verification, right? And the state-of-the-art model here is models like Havorka's model or Dalla-Mann's model, not Bergman's model, because there are some significant limitations to the physiology that it can capture. So what we have already is we can model the insulin glucose dynamics with much better fidelity. So incorporating those models is one thing, and incorporating the control algorithms is another thing. So the control algorithms are now much more complicated. They are what are called model predictive control algorithms, which involve a solver, an optimization solver inside the controller that's running. So at every time step, the controller itself runs a linear programming or a quadratic programming instance. So capturing such controllers is going to be even harder. But so what we have done so far, well, we have taken the top part. That part is easy to do. We have modeled it. We have taken the models from the paper and incorporated it. The bottom part is a really hard problem. Verifying model predictive controllers is really hard. It's going to be the next big challenge if we want to be relevant to the industry, because this is what the industry really wants to use, MPC controllers, because processors are fast and they can solve optimization problems in real time, so people want to use this. And we don't know how to get there yet, but the hope is that we will, using some of these techniques, we may get there, right? So to end this whole long story, CPS are quite challenging and complicated, and everyone says that models of cars, aeroplanes, human physiology, they can be arbitrarily complex, and these models aren't human artifacts really. They are a combination of human artifacts and laws of physics and laws of biology. So it's very difficult to say that they can be as intuitive, and they can, in program verification we say programs have simple invariance, at least for the kinds of properties we are interested in. Those kinds of things one cannot reasonably expect here, but one can expect other things. One can expect to work in continuous state spaces, have continuous sensitivity to initial conditions, have properties like local linearizability, which means if I make small changes to the input, the output changes will be linear in the changes I make to the input, which is a very nice property. Programs generally don't have it because we have if statements that destroy local linearizability. Control algorithms are often designed to stabilize the system. So most of the runs will be stable, a few of the runs will be unstable, so that actually helps us in verification as well, because over time as we simulate longer, the system behavior will get to the stable behavior, and so it's very easy to do verification for systems that are stable. Okay, systems that are unstable, you have to face a lot of other problems, but stable systems are nice and easy, well behaved to verify, at least through simulations. So the hope is that we can exploit these properties and more properties which I haven't mentioned here to make these verification problems easy and make them, even though they are not decidable, the decidable cases might require us to exploit these kinds of conditions. So that's all I had to say, and we have S-Taliro online, so it's available online for you to use, and I wanted to thank you all for listening to me.
Time for a couple of questions.
Yep.
What about abstraction?
Well,
Can you do some abstraction there to simplify the problem?
He does. This cone, the first part of your talk was already abstraction, right? Your temporal logic.
Well, that's an abstraction of the trace. Yes, that's right. Yeah, and it's a very different kind of abstraction. It's not the kind of abstraction we are used to doing, right? I mean, normally abstraction takes a system and gives a simpler system. All we are doing is here we use abstraction of traces to give us a number that says how close are we to violating the property. So that is still an abstraction, but I haven't done abstraction of the system yet. So that would be a nice idea, right? Using solvers on the abstraction to tell us how to start falsifying would be a nice idea. Right now I don't know any I don't have any front ends to take Simulink Stateflow and do some abstraction. So that would be a good place to start for us. And already there are many ideas on if you had abstractions, then how could you use them in falsification? But we don't have any yet. But yes, if you want to think about abstractions in this work, yes, the use of the cylinder around the trace is an example of an abstraction. But it's a different purpose of doing the abstraction than why we do it in normal verification.
What you see is that all this work kind of leverages very highly on the local sensitivity of the function, right?
That's right.
I was thinking about the interaction with the environment, right? So, for example, this function about the more you accelerate, the more likely you are to get to some failure state. But I was wondering if you can input into the measure function, into this distance function, maybe the probability of taking some inputs rather than others. So, for example, in the case of the motor, it might be the case that more people, the more fast they are going, the less likely they are to accelerate more.
Correct.
So if you can adjust the distance function given.
Yes. So we have some ideas of adjusting the distance function. So the way I talked about the distance function, I won't bring that slide up. It's way in the beginning of my talk. It seems like we use this Euclidean metric, but that's not usually done. So we really want distance functions to relate to what this distance actually means in the scale of the system. So I take your question to mean that suppose you have some inputs and that where you may be able to make a big change and make very little change to the dynamics of your system. So you might have.
Maybe I have a trace that is really close to an error, but given what I know about the environment, I know that it's much likely that the trace will actually go far from the error than actually getting closer to it.
That actually brings in, yes, you're right. That brings in the dynamics into measuring. So one of the reasons this was so easy to work, and I guess I should have put a slide on this, but let me try and fish out the slide. Okay, right here. So one of the reasons this was so easy was the robustness computation knew nothing of the system that produced the trace. right? And problem is, yes, that also means that things like what you're saying, you know, like incorporating some system knowledge into how you search is not possible, right? But if you can do that, then you can of course do much better, right? You can, people already know a lot about, you know, how to control systems that are non-holonomic, and people know that, okay, you cannot, you know, even though two states look very close in the distance sense, it doesn't mean that you can get from state A to B. But those kinds of things we can't incorporate in this framework because that requires breaking the box and looking into the simulator and looking into the model. We haven't done that yet. But what you're saying is a very good idea. And that's what we are hoping to try. Yeah. Thanks.
Questions?
All right. Thank you.